Yeah, I don't know. Like this is gonna be magic.
Yeah.
Hello, Professor. I have a question. Can I ask it quickly?
What is MC? Oh, what's that again? It's both. 1 hour of. I mean, she will announce it. Kelly. Can you hear me? Everybody? Okay, I don't even need to use the other mic. Just use this. Oh, you can hear me. Oh, perfect. Okay, you can hear me. You can hear me. It's great. All right. So what's the question? Yeah, the format. Let me just say the format. So it will be a 1 hour of the following short answer. So multiple choice computational, multiple choice conceptual, true false, and then another hour of a long answer. Okay, so 2 hours. Yeah, so the first one will be over Quercus, and second upload on Gradescope or something. Will we have to remember theorems and definitions by numbers? No, you don't have to remember the theorems numbers. You just have to remember the theorem. Like if you're gonna use there just a basis, like that you can extend. So okay, let's. No, you don't have to remember the numbers. Like you can say we learned in class, so or from the book, from the textbook, or from class, and then you state the theorem. So given Li inside V, finite dimensional, we can extend to a basis. So given LIS, we can extend to a basis S prime. So you just state the result, because who's going to remember the numbers? That's crazy. Okay. Okay, any questions? Yes. All right. Let's see how this is gonna work. All right. So the midterm material ends tomorrow. So this is included. And yeah, I know we give you like a week and a half. So it's gonna be rank nullity and inverse and isomorphism. So that ends tomorrow. And then Friday, we're gonna explain that diagram. So you're not tested on this. So it will be up to section 2 point, let me find it. Yeah, so up to 2.6, that's basically your midterm. Okay, not 2.2. We haven't gone into 2.2, so up to 2.6. Okay, okay. All right, let's start. All right, okay, so where am I? Right, so you've seen this for matrices. Let me remind you for matrices. So from 2 to 3, rank of matrix. I can ask people here. Can anybody tell me if I give you columns V1 to Vn, what was the rank of a matrix? Does anybody remember a little bit? Oh, you do? What do you mean by basic variables? Yes, exactly. So for rank of matrix, it's the number of VIs, the maximum number. So you look at overall subsets, there are Li. So let's do some stupid example. 1, 0, 0, 0, 1, 1, 0, let's see, 2, 2, and then 0, 0, 1. What's the rank? I'll ask both. Even in the chat, what is the rank of this matrix? Can anybody tell me? Okay, nobody cares. Yeah, I'll ask you. Yes. 3, right? So let's see, we want the maximum. Of course, these two are Li, but you can add one more. So yeah, 3. Because these two are Li, and then you can pick one of them. So it doesn't matter. That's why it's a maximum. You can have 2 sets attaining it. So either you pick these 3, or you pick these 3. Sorry. Yeah, these 3. All right. So that's rank. And this generalizes for linear transformations, like all the crazy stuff we've done so far. You can still define rank, which will show it's the same as the rank of the matrix representation for your map. So we define rank to be the dimension of the image. Next week, we'll show that this is the rank of the representation. So the thing you learned will agree with this, but this is a proof. And we'll do it next week. So everything will come together. But for now, we'll just work with this dimension. And then when you hear nullity, because somebody asked last time, yeah, so it will just be the dimension of the kernel. So this is a subspace and it has a dimension, right? Yep. Questions? 3. Okay. All right. Yeah, so this is our main theorem, and it's easy to remember, I hope. So it says that, what's a good picture? So this is your V, this is your W, this is your kernel, and this is the image. The kernel gets sent to the 0 vector of W. So it says the size of kernel of T plus the size of the image of T gives you the entire V. Okay. That's my next slide. Can someone tell me why is this? Yeah, well, this is okay. We'll talk about this. But can someone tell me why is this surprising? This result? Do you know? Yeah. Yeah. Go ahead. Yeah. Yeah. Yeah.
I think because you're looking at the dimension of something and your domain and then something.
Perfect.
Codomain.
Yes, exactly.
To give you some information about like the transfer.
Right, right. So if I said something like V and kernel of T and then complement of the kernel of T, you know, like kernel of T, like complement in the space, like, you know, V take away kernel of T, then of course you have dimension plus dimension of the kernel complement is dimension of V, which is, anyways, yeah, because you're working in the same space, so you just extend the basis. But that's not the case here. You're working in the image. So the equivalent question that some people make mistakes on it, some people write this, that kernel of T plus image of T is V. I mean, that's complete nonsense from what, sorry, what's your first name? Well, so for, oh yeah, I know. Will. So from what Will says, so this is nonsense. So this is a counting argument. We're just counting the number of vectors, and we're just saying, oh, the number matches because you have a linear map. So it's not a question of inclusion in one space or another. It's just counting. Okay. Any question from the chat? No. All right. So how do you do this? So again, kernel of T is inside V. So we got to start from somewhere, and we're going to start from this guy, and we're going to build the basis S1 for the kernel of T, and then extend to S. So we're going to add an S2 part, so that the mapped image of this guy would be a basis for the image. So we're going to have that dimension of V, which is the size of S, is equal to the, oh, and they have to be disjoint, of course. And it has to equal dimension of this plus size of this, and this is the dimension of the kernel, and this is the dimension of the image. So we just have to show that. So we're going to play with the cardinality of these sets. Just a cardinality question. Okay, question from the chat. All right. Yeah, so you have to start from somewhere, and we're going to start from the kernel because we are already in the space V. So let's start from there. Now, maybe I can ask you, how do you know that there is such a basis for the kernel? Any ideas? It's a tricky question because it's hard to answer. I'm just curious if anybody has a guess. Do you know or no? Right. So we, yeah. So we proved that for any, so any sub. Do I write it? I hope I write it next. Oh yeah, yeah. I say it here. So whatever. So it's a subset. So it's also a vector space, and we proved the existence last week. So any vector space, any finite dimensional vector space, has a basis. That's always the case because we're gonna do it next week as well. Second proof that you can map any V with dimension n. There's a map called an isomorphism, mapping it to Rn. So there's always a this is called coordinate map. We will talk about this. So you will be able to build a basis out of the standard basis for Rn, which is amazing. So we will talk about all that stuff. But for now, all we're using is that any vector space as a basis. We proved that, so we're just using that. Happy everyone? Yeah, yeah, because it's a subspace, exactly. Yes. I should check the chat. Right. Also, last week we did the following trick. We had the following. So you start with S1, V1 to VK, and then we had a W equal to, yeah, take any W not in the span of S1, and then we proved the following. We proved that span of V1 VK is equal to the span of W V1, remove some VJ VK, right? So we did this trick where we, yeah, we started adding more elements into our span. Okay, anyhow. So yeah, we went from, we wanted to extend to the full space. So we started with V1 VK and we went to V1 VN. So N would be bigger than K or equal. Right? So we make it into a bigger space. What's a silly picture I can draw? You know, suppose you have 3D and this is the kernel of T, then we just add the E3 vector. So you have E1, E2, and you just extend to E3. I don't know, just, that's all. It's not hard. Okay, now what's the hard part? So you gave me some vectors. You gave me VK plus 1 to VN. Show that TVK plus 1 to TVN is a basis for image of T. Yeah. Any guesses? How would you? Because we proved something last week. So I'm just wondering if you have any guesses before we go on. How would you show that? So what did we show about TV1 to TVN? The span of that. What was it equal? Yeah, it's the image of T. So, right, perfect. Now we're saying that even with less of them, you still get the image. So we're saying even if you drop the first K, you still get image of, let me do it this way. You still get the image of T. Okay, so you don't, the other guys are redundant. They are redundant vectors. So the first K of them are redundant. Any guesses why they are redundant here or in the chat? Yes. Perfect. So yeah, we showed last class that is give you the image. And then if you take any guy from V in S1, so TV1 to TVK, these are all equal to 0 because they're in the kernel. I know, it's simple. And yeah, so you can forget this because they give you an L-dependent set. So we got the span. So remember, basis has the following two things: span and Li. So you need both. We showed span. We're going to show a linear independence. Okay. And how do you do it? Well, you assume that you satisfy this. You need to show that AK plus 1 to AN are all 0. then you have Li. Okay. So here's the trick. So yeah, so this is a linear combination. So going from here to here, you use linearity. Okay, so you bring them all in. So what does that imply for this guy? Where is this in? I know. Are my questions too simple? Okay, I'll try to think some harder. Yeah, so it's in the kernel. Right. So it's in the kernel. And we already know what the kernel is. The kernel is the span of V1 to Vk. So this element X is given by some linear combination of V1 to Vk. All right. And yeah, and then I just brought them all. So let me write what I did here. So I brought everything to the right. So you have B1, V1, BK, VK, and then this should be a minus. So minus AK plus 1, VK plus 1, and then minus AN, VN, and they're all equal to 0. Okay, but this is a basis. That's how we build it, which means it's Li. So which means that B1 is equal to B2, which is equal to minus AK plus 1, which is equal to minus AN, and they're all 0. So namely, you got what you wanted, that these guys are 0. So it's a sort of a roundabout argument because we don't have Li necessarily for these guys, but we have it for the basis. So then you have to come back. It's a weird way of arguing. Okay, anybody from the chat has a question? Why were they redundant? Why were they redundant? Because they all get mapped to the kernel. Where is it? Here. So, so the question was, so you have TV1 to TVK, and then TVK plus 1 to TVN. And the question is this Li? And the answer is no, because the first of them are all in the kernel. V1 to VK, so they're all 0. So you have 0, 0, and then TVK plus 1, TVN. Is that okay, Kellyanne? Okay, good. There's a lag. All right. Fine. Yes. So when did we use linearity? Any guesses? There's one obvious one, but I just want to see your understanding. There's many steps. So can you give me like numbers? So yeah, one is here, right? This is easy. And what else? We also used it in the augmentation lemma. So yeah, so let me write it here. So there is no augmentation lemma for nonlinear maps. So I have a counterexample. That's the main reason. You cannot extend the basis. Oops. So so let's look at this map. So this is nonlinear, and it goes from R2 to R. And let's see why it fails rank nullity. So can somebody tell me what's the dimension of the kernel? So you can put the number in the chat, or anybody here. What's the dimension of the kernel? Yeah. What is it, sorry? 2? Why is it 2? So just a second, like, what is kernel? Kernel is all the guys. So it would be all the real numbers. No, all the vectors A, B. So it's the T of A, B is 0. Y- Right. Yeah, it would be, it would, so, okay, let's do it. So what are we saying? We're saying that T of A, B is 0, which means that A times B is 0. So what shall I say here? Yeah, I mean, like, yeah, well, there's so many problems here that you can't even define subspace. So, but okay, so from here, what do we get? We get that A0 or B0. So this is not even a subspace. So, right? So this is but I mean, in any case, no, this is not quite right. So they're both, this is a one-dimensional object still. Like, even though it's like, it looks like this. So I have to think. A0, it's over here, right? Yeah, this is the guy and this is this. So these are one-dimensional objects, okay? Because you can get them from, this is the union of span of, let's see, 1, 0. And then, so I have to write union here. It's not plus. If I write plus, I get R2. Is that clear? If I wrote plus, I get R2. But here we're saying the union. So it's the union of two one-dimensional spaces, which is still one-dimensional. Yeah. So this is 1. And so this is 1. And then what's my question? Oh yeah, but what's the, let me see, what do I want to say? And then the image, dimension of the image of T is, what is it? It's 1, right? Yeah, so everything gets mapped to 1. So you do have rank nullity, even though you have like a crazy map like that. But anyways, so they are, it's not like an if and only if statement. I guess that was the point. Is that okay? Any questions? 1. Yeah. I don't know. I just want to show you an example. But I guess you want an example where it fails. Okay, now I have to think. So let's see. Take something stupid like, let's see. I'll think about it. Anyways. Did we use finite dimensionality? If so, at which steps did we actually need our guide to be finite dimensional? Is this statement true for infinite? So if dim V is infinite, could it still work? So let's look at our proof. So, I mean, that's the meat of the proof. So any guesses where we use finite dimensional? Let me take you where we're actually kind of using it. Any guesses? Like where are? Yeah, so in this augmentation lemma, we did this bootstrapping argument where we kept adding vectors. So unless your space is like countable, you don't know if you can even do this. Like if you have something like, so R infinity is fine because each time you're just looking at a different component. But if you work with like continuous functions, then you don't know where to go next. It's called axiom of choice. And it basically says that there's no canonical choice. You have to like do some set theory crazy stuff. But okay, in our world, you cannot do it for uncountably dimensional, but you can do it for countable because each time you just add a vector. So in fact, it is true. They call it countably, so countably infinite. So we're not going to go into this, of course, but spaces like R infinity, and all you're saying is that dimension of kernel of T plus dimension of image of T is infinite, which implies that either one of them or even both is infinite. So whenever you see somebody telling you this is happening and you have some linear map, let's say V to W, then either one of these has to be true. Okay, now I have to give you an example. So let me see. Take V to be the space of polynomials on R. Take W to be R, and take T to be the evaluation map. Okay. All right, so this guy just evaluates your polynomial at 1. Dimension of this guy's of V is infinite. Does anybody know why it's infinite? Like offhand? Here or in the chat. Why is it infinite? Huh? It's obvious? Okay, wait. Yeah, but maybe I'm overcomplicating it. This is the span of 1, x squared. It's just there's infinitely many of them. That's all. Is that okay? Right. So then what's the kernel of T1? When which polynomials in this P infinity get mapped to 0? You know what? Let me simplify. Let me call this. Yeah, because it's a little bit complicated. Let me call it. There's a way to do it this way, but let me do it that way. I think this is a little bit easier for you. So okay, now which ones are these? I think this is a bit easier. What polynomials give you that? So this says that T of 0p. What is T of 0p? It's the first constant in your polynomial, right? So it says that the P0 is 0. So basically you have x, like P1x, P2x squared, P3x cubed, so on. So the kernel has infinite dimension because you just removed me the first constant. So this is the span of x squared. So we skipped 1. So dim of kernel of T 0 is infinite. I don't know. It's just to show you that things still work in countably infinite vector spaces. Yes. That you have a countable basis.
There's like some kind of mapping to that.
Yes. Yeah. In this case, the mapping will just be the you map the exponents of the powers to like, yeah, to whatever, to like 1 gets mapped to R, then R2, R3, R4. We'll do this. Yeah. Okay, questions? Does the rank nullity ever fail? It does, and I will give you a good example. I'll find a non-linear example. But the only reason it fails is because you don't have linear maps. Infinite dimension still works. That's the lesson here. So it fails for non-linear maps. And I thought my example, I have to find a good example. What else? Did we assume the kernel is non-empty? No. So the kernel could be empty. And so it works, namely, it works for injective maps. So yeah, so no, you don't need, the kernel could be empty. All right, moving on. All right, let's do questions. So it works for all linear maps. Yes, you just need, yeah, you just need linear maps. You don't even need finite dimensional. All right. This guy here, what does it do? It just projects on the first component and on the first column vector. I think linear is easy. If you want me to do it, just tell me. So you just, yeah, I mean, you just component addition for the vectors. So, okay. Now let's figure out the kernel. So it says, figure out all the matrices A, C, B, D that are equal to 0, 0, which is the same as asking that AC is 0, 0. So any guesses what's the span here or in the chat? Like what's the kernel of T is given by what span? Of what kind of matrices? There's 2 matrices. Yeah. Perfect. Perfect. Thank you. Is that okay with everybody? Because the the first component just kills off the AC, but then you're left with free variables. And there's only 2 of them. So then you can have, you know, you can have them be like 1 and 1. And if you want to get it, you just add them. So you have A times that, B times the other, or B, and then D. And that will give you 0, 0, B, D. All right. So what's the dimension of the kernel? Yeah, 2. I don't know, I'm just wondering. It gets into your memory when you get tested every 5 seconds. All right. So now I don't have to find the dimension of the image, which is a pain. So dimension of image of T is equal to the dimension of whatever. So I want to do it for N. Okay, whatever. Let me do it for this. 2, and then dimension of the kernel. So first guy is 2. What's the dimension of 2 by 2 matrices? Huh? What's the dimension of when they say, yeah, I meant 2 by 2. Thank you. But I could have made it work for N by N. I would just have restricted the first column, but it was too much computation. So what's the dimension of 2 by 2 matrices? You have to know this. What is it? Is that okay? Do you guys know how to get it? Can I get like a no or a yes? Oh, you don't? Okay, yeah. Let's do it. No, because you like we have a midterm next week, so I need to make sure you're all on the same page. So dimension of M2R is 4. And why is that? Because you can get it from the span of 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0. If matrices confuse you, oops, you can use just for your own, because we haven't proved it yet, you can use for yourself the following isomorphism. M n cross n is isomorphic to R n squared. Okay, so when people write M44, this is isomorphic to R16. So the dimension of n cross n would just be n squared. Okay, that's the general formula, and you're free to use that. And the way we get this isomorphism is we go column by column. Like, yeah, so yeah, we do what is called the snake isomorphism. So you go like this, and you form a R n squared vector. We'll do this. I want, yes, go ahead. For any what? If the dimension of the vector space is n, yep. Yeah. The dimension is an isomorphic invariant. And the reason is because isomorphism sends basis to basis. So the cardinality of the set gets preserved. I mean, we're looking ahead a little bit, but yeah, that's everybody happy? Yes, it's 4. Yes, I should check the chat. All right. Yeah, okay. Let's prove some results. So, yeah, somebody might ask you on multiple choice, is this map injective? And maybe they give you the dimension of the guy or the dimension of the image. So that's a sneaky question, right? They might ask you, show me this guy is injective if dimension of V is equal dimension of image of T. Okay, anyway, so let me, do I have it here? Yeah, okay, so let's do step by step. So first we're going this direction. Injective implies that the kernel has dimension 0. So let me remind you what injective means. So injective means if V1 is not V2, then the images are also not equal. That's injective. Okay. All right. Right. Now suppose you have TV is 0. Yeah, so TV is 0. But then this is also equal to T0 of V. Okay. So here's the sneaky part. The contrapositive of injectivity is that TV1 is equal to TV2 implies V1 is V2. So here you get that V is equal to the 0 vector. So this is the contrapositive. I mean, if that is too much logic for you, let me do it another way. Suppose V is not 0V, then let's use linearity. So you have TV is equal to 20V. So bring them to the left. And what do I want to say? Whatever, I'm overcomplicating stuff. The stuff I wrote here is nice. So if V is not 0V, then you will get that TV is not T0V, but this is 0W. But this is also 0W, which is a contradiction. Is that okay? Yeah, I will stick to contradictions from now. Well, I think they're more contrapositive can be confusing, even though you can get nice proofs from it. But I think teaching wise is better. So the inject. Okay, will we be expected to know the dimension of matrices that have trace 0? Matrices that have symmetrical? Yes. So I think I did some examples. But yeah, so yeah, injective ones 1-to-1. But just a second. So that was a good question. So suppose they ask you find dimension of let's say 0 trace matrices. So M in Mn, so the trace of M is 0. One quick way to do it, hopefully you remember, is what? Do you have an idea? There's a trick we do with this stuff. You go ahead, yeah, whatever. Yeah, it's a square matrix. No, now you're trying to prove it, but there was a quick way to get this. No, okay, you write it as a kernel of some linear map. That's the trick. And the linear map here, it's just the trace map. Okay. What? And then, okay, you still have to like, because like you don't even know if this is a, you don't even know if this is even a subspace. So okay, let me be clear about something. When you compute dimension, you have to make sure that your guy is a subspace. So first you have to do this, then we have to do what Parth said. So here you have, you know, n free variables. Okay, because you have A11, A22, all the way to A and N, and they're all 0. So the dimension will be N. I don't know, okay, I mean, all right. So we showed that injective implies that the only element is the 0 element, and by definition, dimension of the 0 vector is 0. All right. Now assume the opposite. Dimension of kernel of this guy is 0. We want to show that it's injective. So we want to show that TV1 is not TV2. So what do we have? We have TV1. So assume otherwise. And then you use linearity. So that implies that V1 minus V2 is in the kernel of T. But the kernel of T is one dimensional. So it only has one element, the 0 guy. So you get that V1 is equal to V2 plus 0. So V1 is V2. I mean, this is your first time seeing these proofs. So as we go into deeper into the course, you can skip steps. I mean, you don't have to do every, like I'm doing it. Like, yeah, you can skip some of the middle steps. It's fine. Questions? You lose 1 degree of freedom. Yeah, okay, thank you. Yes, that's right. It's n minus 1. Thank you. Yes. All right. All right. And What else? Oh yeah, and but also you can use this to get so let me see. So here you need the spaces to be the same. So if I should have added here. So V is W. So if you have that V is W, you can also show that if your guy is injective, is also surjective. Okay, so when so you have V to W, V to V, and dimension of kernel of T is 0, if and only if surjective and injective. Okay, so so we will see this tomorrow and next week, that if you want to prove something is an isomorphism, you just have to check that the dimension of the kernel is 0. So this is a bijection, that's what it's called. So when you have both, this is called bijection. Okay. And this if and only if we use the rank nullity. Is that okay? Questions? All right. All right. Yeah, so if dimension of V is bigger than dimension of W, can we have surjective? Let's say strictly less. So if they're equal. So can we have surjective? Sure, we can. Why not? So let's look at the previous example. We took A, B, C, D, and we mapped it to AC. And the question is, can we cover R? So you map this. What do you map? You map the 2 by 2 to R2. And what does it mean to be surjective? Well, in our case, it means you can obtain the basis vectors. So just take take 1, 0, 0, 0 and 0, 1, 0, 0, 0. They get mapped to 1, 0 and 0, 1, which is the basis for R2. So yes, in some cases. Okay. All right. What about in the other case? Can we have it? Can we have surjective when dimension of V is less than dimension of W? No, right? What's a quick way to see it from what we proved? What do you think? What theorem will imply this immediately? There's only, yeah, yeah, the only theorem we proved today. So we have that image of T is less or equal than, okay, dimension. Is less or equal than dimension of image of T plus dimension of kernel, which is less or which is equal to a dimension of V, which is strictly less of dimension of W. So you cannot have these two to be equal. That's it. So this can be like short answer stuff. Like they ask you, can this happen? Can that happen? And then you just write this one liner and that's it. Okay. All right. So yeah, we're done. It's 10 o'clock. Okay. Thank you. Any questions? Yes. Thank you. Thank you. Thank you. I didn't understand the answer to the last question. What was the last question? Oh, surjective means the dimension of the image is equal to the dimension of the codomain. But here, this can never be true. So it's wrong, right? Yeah, you can never have surjective.
Hello, Professor. Can you hear me?
Is that okay? Do you guys have questions? Is that okay? Yeah, go ahead.
I just lost like this proof right here. Where are these bees coming from?
So,
Like, where did we introduce those?
right. So this guy X is in the kernel,
Right.
and the kernel has the basis v1 to vk from some existence result.
Yes.
So then that means X. Well, let's forget
Oh,
it.
these are some coefficients.
These are some. Yeah.
So okay, so we have. Okay, so this is in the kernel, and so therefore it's some linear combination. Okay, I see. I got it. Okay.
Okay, yeah, cool.
Yeah.
Thank you. Bye, guys. Welcome back. Good to see some faces. Can we have it equal for the less than or equal? What do you mean? Have it for the less than? Yeah. Have it for the less than or equal. Oh, yeah, but it will only work if they're equal. So if dimension of V is dimension of W, yes. And also, like, we can only have it in this case, but not when you have sharp. Is that okay? All right. Yeah.
Yeah, bye guys.
Any more questions? Is there anybody here? Oh, all right.